Cool. So, hey everyone, thanks for coming and welcome back to the Deep Learning Theory seminar of this week, Halloween Day, which no one called it that. So today we have the pleasure of having Davide Murari. So Davide is doing his postdoc at the University of Cambridge, and most of his research, with this exception of this paper, is on the interplay between dynamical systems and like deep learning. So today, though, he's going to be speaking to us about actually, in some ways, a very related topic. In some ways, yeah, the approximation theory of 1-Lipschitz ResNets. So, after you,
Thank you very
David.
much. Yeah, it's not really an exception in the sense that the first part of the talk, I will motivate the architecture we studied through dynamical systems. So
Yeah.
thank you. So yeah, today we'll present some results that we recently got with Takashi and Carola. And if you're interested in the paper, there is the preprint that you can find here. And I will focus on a particular kind of constraint that we enforce on ResNets or neural networks more generally, which is a constraint on the Lipschitz constant of the network. So first of all, I want to give a brief motivation of why we even care about this kind of constraint and why it's not so easy to enforce it without restricting excessively the expressiveness of the network. I will provide an example, an application that I've been working on pretty extensively in the last 2 or 3 years, which is networks which are 1-Lipschitz for improved robustness to adversarial attacks, for example. And then in the second part, I will focus on this approximation result we worked on. So being interested in, should we be interested in 1-Lipschitz neural networks? And I want, first of all, to anticipate that when I talk about 1-Lipschitz, I always think in this talk about 1-Lipschitz in the L2 norm on linear spaces. So it's quite a particular notion of being 1-Lipschitz. Would be nice to extend this to metrics, general metrics, or manifolds, but this is what we are working on here. And there are several kind of applications where these constraints is desirable. And the first one, as I anticipated, is to control how sensitive is a neural network or a map to perturbations in the input space. And in particular, those which are built adversarially to fool the network, for example, to misclassify a stop sign as a green light, just adding a sticker, I don't know, on top of the sign. And of course, that's not desirable. Other kind of applications are all those situations where we are interested essentially in modeling in a feasible way the set of 1-Lipschitz functions. For example, when interested in modeling or approximating the Wasserstein-1 distance between two measures. And if we are able to parameterize this set through a flexible enough set of networks, then we essentially turn this into a feasible problem because the optimization is on the parameter set rather than the set of functions. And another one which I'm really interested in, and we have done some work on, especially in connection with inverse problems, is whenever we are interested in using neural networks to model or approximate maps which are meant to be iteratively applied on an initial condition. For example, when learning an optimizer, in plug-and-play algorithms for inverse problems. And if we want to get some convergence guarantees, then it's meaningful to control how expansive is our map. So in principle, enforcing this kind of constraint on a generic neural network is not so complicated, at least at a high level, theoretically, because 1-Lipschitz functions have a very interesting property, which is that they are closed under composition. So this means that we don't have to design an overall complicated neural network which satisfies this property out of the box, but we can just compose a lot of simpler transformations, which are the layers of the network. And then if they are well behaved, then so will be their composition, in the sense that two functions f and g with Lipschitz constant lib f and lib g. When you compose them, you can at least provide a coarse upper bound on the Lipschitz constant of the composition by multiplying their Lipschitz constants. So at least with MLPs, which are just alternations of a finite number of affine transformations with usually component-wise nonlinearities, we can generally have a very simple procedure, at least theoretically, to enforce this constraint, because Most of the activation functions are 1-Lipschitz in the absolute value, the metric defined on R. So any kind of activation you want is essentially compatible with this. And then one could essentially control, for example, the spectral norm of the linear part of the affine transformations using something like projected gradient descent while training them, and controlling the leading singular value with power method, for example. And then we can get this constraint. So in principle, it's not a hard challenge, at least to design them. To train them is a different game. I will not go into this today, but even more, if we focus on ResNets, which is the networks I'm mostly interested in, this approach is still feasible, but it becomes more complicated. And that's simply because of the main feature of the residual layers, which is that they don't rely on a parameterization of the full map, but of the residual that this map has with respect to the identity. And the identity is, of course, playing a big role in the Lipschitz constant of the map, because if we are not aware of any particular structure of the map we add to the identity, then generally the best thing we could do to control from above the Lipschitz constant of this layer is triangular inequality. And this inequality cannot provide a better bound than one. So it's hard to just design 1-Lipschitz ResNet layers only thinking about the generic update of the identity or additive perturbation to the identity. And this is even worse, of course, if we compose a lot of these layers, because this grows exponentially if we multiply a lot of these values larger than one. So the idea is that either we give up on building ResNets, which are 1-Lipschitz, or we design f theta in a sensible way somehow, so we could still get it to be 1-Lipschitz. And this is where the point of view of neural networks as discrete dynamical systems or discretizations of the solutions to ordinary differential equations could be very useful, because there's a lot we know about gradient flows, for example, or particular types of dynamical systems that are known to be non-expansive, in the sense that if we start from two initial conditions at time zero and we flow along the solutions of this vector field, then we will end up at any future time not farther than we were at time zero. So we are 1-Lipschitz in the flow map. And the interesting thing is that for negative gradient flows of C1 convex functions, there's a very well-developed theory because of convex analysis, optimization theory, for example. And it's quite easy to see that the exact solution or the flow map of these vector fields is a 1-Lipschitz function for any time t. And you can see it just differentiating with respect to time, the squared Euclidean difference between any pair of solutions. And just because of the convexity properties of V and being V C1, we can say that this is non-positive, and hence the distance will not increase with time. So the exact solution of these systems is 1-Lipschitz. So we could try to leverage this knowledge to design layers. It's a big jump at this stage, but I will clarify it in the next slide. We could try to make use of this knowledge to design our ResNet layers so they are well behaved with respect to the desirable property we want to enforce. In fact, what we can do is essentially just say, okay, V has only to be convex and C1 in order for this flow map to be 1-Lipschitz. So we are also allowed to parameterize it in a meaningful way. So it's also compatible with what we're used to in neural networks theory. So if in particular we design the potential to be based on ReLU squared, it's just a convenient choice, but it could be any convex function essentially, and C1. ReLU squared divided by 2 for convenience, and we apply an affine transformation of the input. Then if we take the gradient of this, then we recover essentially a very standard single hidden layer ReLU network where the weights are tied. So instead of having free weights inside and outside of our transformation of our ReLU function, we have that one is the opposite of the transpose of the other. So simply by constraining the weights in this way, we have a symmetric Jacobian in our network, in our vector field, and hence it is a gradient. And because of what we saw before, this is also, at least when exactly solved, leading to a 1-Lipschitz flow map, a
Uh,
1-Lipschitz solution. Yeah.
can I ask one silly question?
Yeah.
So I guess if you use it like the integral representation of the OD, like, do you really need like a C1, or can you get away with Lipschitz? Like
No,
just
yeah,
Lip?
yeah. Yeah, Lipschitz is enough because
Okay.
then you can use the subgradient, and
Yeah, yeah,
that's
okay, yeah, yeah,
also
yeah.
that's also satisfying all the properties.
Cool,
Yeah,
cool,
yeah,
cool.
it's only convenient. Yeah,
Yeah, yeah, yeah, just to get this check. Cool, cool.
yeah. And then the interesting thing is that for those especially familiar with the structure preserving numerical methods, like symplectic methods, for example, for Hamiltonian systems, it's not so surprising the fact that if a dynamical system has some properties and we use any numerical method to approximate its solutions, we might break them. So what we want to do now is try to approximate the solutions of this system because we know they're well behaved for our interests, but doing so while preserving the 1-Lipschitz structure. And in this case, we are quite lucky in the sense that the simplest method, which is the explicit Euler method, up to a restriction on the step size, is able to reproduce this property discretely. So if you approximate the solution of this vector field, doing one step with the explicit Euler, which is this method here, which is the first we learn, um, if you take the time step tau, which is small enough, in 0, 2 over the Lipschitz constant of this vector field, which in this case is just the squared spectral norm of the weight W, then you guarantee that also discretely your map is 1-Lipschitz. And if you have never seen the connection between dynamical systems and ResNets, this is the easiest way to see it, in my opinion, in the sense that ResNets are exactly an additive perturbation of the identity, where the additive perturbation is the parametrized part. So we could just think of a single layer of a ResNet as an Euler step of a suitably defined vector field. And in this case, we define it in this way. Okay. So this map is by construction 1-Lipschitz, and just to convince yourself that this is true, I just created a very simple example where I consider an orthogonal 2 by 2 matrix, which is this one. And then I took a bunch of initial conditions and applied this Euler step, a single Euler step with a varying step size. So in this case, the spectral norm is 1. So the bound we allow in order to guarantee 1-Lipschitzness is 0, 2, the interval 0, 2. And in fact, you can see that the ratio between the distance at time t and the distance at time 0 is controlled by 1. So it's non-expansive map if you take a time step up to 2. Otherwise, you are allowed to expand, even though the original system is non-expansive. Okay. So all this work is essentially helping us to define a family of neural networks that resemble conventional ResNets, but whose layers are associable to gradient steps. And this naturally leads to 1-Lipschitz property on the residual layers. And as for any kind of neural network, we could also combine these layers with affine transformations, any other trick we might want to, up to excluding those that break the Lipschitz structure, of course, if we actually want an overall network that satisfies this property. But for example, if we have just affine transformations, that's not really a problem, up to controlling the spectral norm of the Jacobian of these affine transformations. And if you prefer to think in terms of continuous dynamical systems or neural ODEs, which are kind of an alternative viewpoint to this procedure we have gone through, you could also think to have a neural ODE in between the two affine transformations, which is a gradient flow. Okay. Now, just to show a couple of experiments, numerical experiments that we did in the past with these kind of networks before studying their approximation properties, I want to focus on 1-Lipschitz networks for robust classification. And I'm sure that we have all seen what's the classification problem, but I want just to put down some notation. So the goal of building a classifier is, of course, that we are provided with a data set of inputs, images, for example, that are drawn from a certain distribution supported on a set X. And we know that they should be divided or partitioned into C classes. So the goal in this case is just to define a network going from RD to RC, where the last layer is like a normalization layer, like softmax. And then in this way, we could interpret the highest entry of the output of the network as the most likely, the class that the network thinks is the most likely one for the input, essentially. So this task is something that we know quite well how to solve up to having a good enough data set. But at the same time, it's also very easy to fool these kind of networks and make them misclassify inputs, which for us are essentially undistinguishable from the original ones. But for the network, they are entirely different, completely different. And there are several reasons why this could be the case. But a simple argument could also be based on Lipschitz constants that I'm going to go into in the next slide. But just as a couple of examples, in this case, you can see an image from the CFAR10 dataset, so one of the simple benchmarks. And this is the image of a horse. I trained a ResNet with no constraints, which was, I don't remember, 93% accurate, something like that on test images. So this was correctly classified, but then just building a perturbation of control the spectral norm, 0.3, and which for us leads to x plus delta, which is essentially undistinguishable from the original image. This was classified with also very high certainty as a dog, differently from the one on the left, which was a horse. And the same thing could also be done on graphs, for example. This is not so imperceptible for us now, but it's just a simple toy problem. And the idea is that one could adversarially add edges or modify features in a graph, and the same kind of goal would be relevant here to try to build networks that are robust to this kind of adversarial modifications of the input. Now, in order to relate this with the Lipschitz constant more rigorously, we need also to couple the Lipschitz constant with another concept, which is the notion of gap or margin. And I will just try to go quickly through it now. So let's think for a second about a very simple problem, which is just classify inputs into three classes. We don't care about what are these inputs, just three classes. And we train two networks, which are at the end of the training, and θ1 and then θ2. So say that then we provide a test image, test input X, which is known to belong to class 2. So we expect that the second entry will be the highest one, and both networks do that correctly. But it's also quite intuitive to see that the first network seems a bit less certain somehow about its prediction because of the reduced gap in between the highest and the second highest entry, which is much, much smaller than the one for the second network. So this intuitively tells us how robust it is in the output space, our network. But it's not enough, because it could be that this network is very sensitive to perturbations in the input, so that's not enough. So a mathematical framework that could allow us to combine this Lipschitz constant, sensitivity in the input and gap in the output, is an inequality like this, essentially, which relies on the concept of margin, which is just a formalization of the notion of gap I intuitively introduced before. And the idea is that if a network has a good trade-off between margin and Lipschitz constant, then we can actually guarantee the robustness within a certain ball around centered at the test points of our neural network. In the sense that we classify all the points in this ball as the center up to a radius which is small enough somehow. And this small enough depends, of course, on the trade-off between the two constants. So then the idea is that if we want to improve the robustness of a network, we could just try to train it so it maximizes the margin and also have a control on the Lipschitz constant of the network. So just to give you an idea of what the architecture we saw up in the first section of this presentation can do in this task, which is just a simple toy problem. It's fashion MNIST. You can see that if we train a neural network which has a constraint Lipschitz constant, this gradient-like neural network we saw before, and you compare it with a ResNet, which has essentially the same kind of architecture, but where you don't tie the weights. So instead of being minus W transpose and W, they're just P and W, okay? So you get a slightly better accuracy on clean images, so with zero perturbation. This is not so easy to appreciate for this simple test problem, but it's much worse if you if you make the dataset bigger or more complicated. So there seems to always be in this kind of problems, kind of a trade-off between being robust and being accurate. And that's also what motivated me to study the approximation properties. But then you can see that if you increase the perturbation of the adversarial attacks that you apply to the trained networks, so if epsilon is larger, then you essentially perturb more the test images. Then you expect some kind of drop in accuracy, but you would like a milder one. And that's what we get with the non-expansive network, with the 1-Lipschitz network we saw before, whereas the ResNet has a much quicker drop in performance. So this is just a simple example. In this paper, we studied a few more, also related to inverse problems. But it's just to show that at least these networks, they are not just completely strange, they still train. And they also improve the robustness of the network if controlled and trained properly. But this kind of reduction in accuracy on clean images is, as I said, it's quite a common trend. I've done a few experiments in different projects, and it's quite common. So I was motivated to try to understand if this is like an intrinsic limitation of 1-Lipschitz ResNet or 1-Lipschitz networks that they cannot actually approximate these kind of functions, or if it is more like a problem of how we are training them. And that's why I moved into trying to understand the approximation properties of these models. So, and this is the main content of the paper I want to present now. And the idea is that we essentially want to understand what can be approximated to arbitrary accuracy with the networks that I introduced in the first part. And since this is a very structured problem, a very constrained problem, we started with scalar objective functions, scalar target functions, in the same way as similar papers studying MLPs and density of MLPs with constrained Lipschitz constant do it. Of course, this is a clear limitation, and our goal will be to try to extend this to higher dimensional outputs. So let's put down a few more details, mathematical details now. We have a compact set of RD. D is the dimension, and we fix the output space to dimension c equal 1. And we define our set of functions, which is gd of x. And it's just obtained in the same way I wrote before. So it's an affine transformation that essentially lifts the dimensionality from D to H. Then there is a finite set of residual layers, which are gradient steps in this case. So EH stands for the set of gradient ResNet layers we saw before. And then we can project at the end to the scalar output. Okay. So in this case, I want to stress the fact that we are leaving Q and pi unconstrained. So these are not necessarily all 1-Lipschitz functions. We can actually fairly easily constrain them. Q and pi can be constrained so that overall we get a 1-Lipschitz function. But the ways we are aware of don't allow our proof to go through, essentially. So we cannot guarantee that these explicit constraints lead to universality. We can do that constraining pi. But still, this is not a problem because I will show in a second what we prove, essentially, in this case. And we denote with C1 of xr just the set of 1-Lipschitz functions from x to r. So what we prove, the first universal approximation theorem that we worked on, is that the set GD intersected with the set of one Lipschitz function. So we are not allowed, even though we don't have an explicit constraint for Q and pi, we are not allowed to get anything which is not one Lipschitz to go through this proof, is dense in the set of one Lipschitz functions from X to R. So density meaning just that for any G and for any epsilon, we can get epsilon close to G in the supremum norm. Now, this is the first result we worked on, and to get a much more deeper understanding of this kind of this set of functions, which at least originally seemed a bit obscure for us, we went through two different complementary proof strategies somehow. One is more like an existence result because it relies on a very strong result, which is a variation of the Stone-Weierstrass theorem adapted for one Lipschitz functions rather than continuous ones. And the other one is instead showing what are some of the elements contained in our set of functions to try to have a better understanding of what we're working with, essentially. So I will not go through the first proof because this proof is essentially informing us that our set of functions, our set of networks is a lattice, so it's closed under max and min, and it also separates points. So this is simply means that you can find a function f that gives different values at different points, essentially. You can see it written here. And this is quite informative because it tells us a little bit about the structure of the set. But we weren't so satisfied with this because it doesn't really provide any example of function contained in this set. So then we went through a bit more of analysis, and we understood that essentially all the piecewise affine one Lipschitz functions are contained in our set. And the interesting thing is that since we work with ReLU, our set is also made only of piecewise affine one Lipschitz functions. So this is essentially leading to a characterization of this set. And then one can conclude by the density of this set in the set of one Lipschitz functions. So now I will go through this second proof because I think it's quite informative. And to do this, we needed one of the several representation theorems for piecewise affine functions. And there are many of them, like difference of convex functions or max min representation. That's the one we are using. And then we essentially show that this representation for any choice of parameters belongs to our set. So the first, this is just a repetition of what I already said, but what we do now is rely on this max min representation of piecewise affine. One Lipschitz is just an addition we make here, but this representation is true even without the one Lipschitz, affine scalar functions. And this tells you essentially that for any function having these properties from Rd to R, you can find a suitable collection of vectors, Aij, and biases or shifts, Bij, so that f of x is exactly equal to the maximum of k functions, where k depends on the function, of course, and the dimension d. And all of these functions are obtained by computing the minimum of affine pieces. This Aij in or less or equal than 1 is just because this provides essentially the pointwise Jacobian, the gradient of our function, and being it one Lipschitz, it must be with this constraint. So now I will show you that these functions belong to our set. And first, I want to provide a visual understanding of the proof, which after we have done it, it seems quite simple. At the beginning, it was hard to get here. But the main idea is quite straightforward, I think, because what we do, at least in this first result, is say, let's use the first affine transformation, Q, to extract all the affine pieces we need. So we know that any function f, which is piecewise affine, it must be the maximum of the minimum of affine pieces. So let's first compute them all, and then let's combine them properly to get our target function. So we first get a hidden dimension h, which depends on the number of affine pieces. Then we define a first block of residual layers that somehow combines them properly to extract f1 to fk, and then a second block of layers that computes the maximum. Okay. so that overall we get up to a projection, the desired function. So to do this, we heavily use the properties of the ReLU function. That could be seen as a bit of a limitation somehow of the approach. I will comment a bit more on this at the end. And the first property is that this can be like the identity map is exactly representable with ReLU, and that's mostly useful because then you can essentially assume that any pair of ReLU networks has the same number of layers. That's more the main, the key takeaway of this property. The second one is positively homogeneous. That's very convenient for us. And then what led us to think of the max-min representation is that you can exactly write down the max and the mean between any pair of inputs, and also of vectors if you only want to do it entry-wise, of course. So then, based on these properties, we can extract all the kind of pieces that we are interested in. Because what we can do is say that, first of all, the first affine layer Q has to extract all the affine pieces, as I said. So it computes all these inner products. And this is the key point where we are not allowed to have constraints on the number of Q. That's going back to the lack of constraints I commented on before. Because at least proving the theorem in this way, then we are relying on the fact that we are actually able to extract all the pieces at the first step. And this is not possible despite all these rows, A, I, J, being 1-Lipschitz maps somehow, because they are all constrained in norm. But then you get a matrix having all rows. The row-wise L2 norm is constrained by 1, but then the spectral norm is not constrained by 1. So that's the main bottleneck somehow. So it would be nice if we managed to find a workaround, but probably that implies having to restructure a lot in the proof, of course. But I will show in the second part of this proof or this theory part that we can actually do that, adding some layers. So H, the hidden dimension, is then constrained by the number of affine pieces. That's the limiting factor here. And then we realize that our residual layers, if you choose properly the weights, can represent a function which is similarly simple, but which is a fundamental building block if you want to compute the maximum of affine pieces and the minimum of affine pieces. And this was the big surprise for us and what started essentially all the analysis. Because if you just fix the weights W, so they are -1, 1, and then the factor over square root of 2 is just to ensure the norm is compatible, but that's just because ReLU is positively homogeneous. So the 2 here compensates for the square roots here. So we wouldn't like it there, but it's just possible to do it anyway. And the interesting thing is that this is exactly a gradient step as we interpreted this before, with bias which is set to 0 and weights which are of norm 1, which is totally fine given the constraint on the time step, which is exactly equal to 2 over the spectral norm. So these are 1-Lipschitz. We know this is 1-Lipschitz. It's just fixing all the components but the first 2 which are ordered. So it's a 1-Lipschitz function, and we show it can be written in this form. And then I didn't write the conclusion in the slides, but the idea is quite simple from here, because once you're able to do this and you already have all the affine pieces, you just need to properly combine them, and either sequentially, and then you have a very pessimistic depth control on the depth, or in parallel, and then you have a log factor essentially that leads to the complexity in depth. You can combine all the affine pieces so to extract exactly what you want. Now, this result is satisfying in a sense because it provides some insights on the architecture that we started from, but at the same time, it lacks explicit constraints on the affine layers. So that could be a problem from the implementation point of view if we want to actually guarantee this function is 1-Lipschitz and also dense. and then it has no bound on the width. Okay, so both unbounded width and depth. So then we try to understand what happens if we fix one of them. So we then studied layers with bounded width and unbounded depth. And of course, if we follow this idea, we cannot actually proceed in the same way as before, because the width was determined by the piecewise affine function. And the piecewise affine function depends on how accurately you want to approximate the 1-Lipschitz function. So that's exactly what we want to avoid. So we have to modify quite a lot in the proof. But not only that, we also had to change a little bit the set of functions that we are interested in. So now we introduce a new family of ResNet-like architectures, if you want, which are essentially as those we saw before, but we interleave the residual layers with affine transformations. So the phi thetas are exactly as before, with some constraints I will comment on. And the affine layers in between are, in principle, they could be allowed to be free, but then we would have to intersect this set again with a set of 1-Lipschitz functions. But then we also found out explicit constraints on all these pieces, so that overall our set of functions is made only of 1-Lipschitz functions. So in particular, we had to constrain the residual layers, so they are not just any gradient step, but the first three components are particular type of gradient step, and the remaining ones are generic. Okay, this is only because we want an explicit constraint, but if we allow for the intersection, and we'll comment on later, this could be any gradient step we discussed before. And also the affine layers here are, in principle, they could be allowed to be free, of course, but if we provide a specific constraint, then we can guarantee that overall they compose well while not breaking the 1-Lipschitz structure. And this means in particular that you have some constraint on the block rows of your matrix. This notation here, just to comment on briefly, the tilde here simply stands for the fact that these are the affine transformations associated with these linear layers, okay? But the structure, the real constraint is in the Jacobian of the affine transformation. So then what we did is study this class of functions as before, but the first result, which we could prove and we couldn't in the other setup, is that whatever choice of weights within this constraint space, you still get a 1-Lipschitz function. So you don't have to intersect it with the set of 1-Lipschitz functions. So this could be practically more relevant for applications. And the second aspect, which is the fundamental one for this universality result, is that each and every piecewise affine 1-Lipschitz function again belongs to this set up to when h is d plus 3. So if the input dimension is d and we allow for at least d plus 3 hidden layers, then we are done. We are good enough. Of course, if we take more than this, that's fine. It could buy us some efficiency in depth, but our proof relies on the worst case scenario, d plus 3. Okay. So again, the universality immediately follows from here, but I want just in the last couple of slides to comment on how we get away with this bounded width and how we then compute our affine pieces, since we are not allowed anymore to pre-compute them at the beginning. And to do this, I will work through an example because the proof is constructive essentially as before. So I think it's quite insightful to look into a simple example, which is representative, not just a particular one. So let's think to be interested in approximating or representing, this function, which has four affine, in this case, linear pieces, just for conciseness, which are based on four vectors, A1, A2, A3, A4, and you take the maximum between the two pairs and then the minimum of these results. Now, the idea is that since we cannot compute all the pieces at the beginning, we need essentially some memory. We need the memory of the input that goes through all the depth of the network, because then we are able to compute these pieces online. So as we need them, we can recompute them. And that's why we need at least D layers. D because the input has dimension D. Now, if we only had to compute the maximum or the minimum and not a combination of them, we wouldn't need the third additional layer. We would just need D plus 2. But the plus 3 is because in our proof, this neuron here is essentially meant to be a memory of the previously computed maximum if we want to compute a minimum of them, essentially. Is a running memory of the work we have done up to now. And the first two components instead is where everything happens. So it's where the maximum and the minimum are computed between the pieces we need. So for example, if you have X, you first compute the first two pieces, A1 transpose X, A2 transpose X. Here you can put whatever you want. And this is the memory. And there's the first residual layers, which computes the maximum and the minimum. We don't care about the minimum, but that's automatically done with this map. And then A1 is just essentially putting order in what we have and also computing the new pieces. So it computes A3 transpose, A4 transpose, and it puts in the memory what we wanted. So this is the piece we wanted and is stored here. And then again, we do the same. So max min, and then we can just arrange them properly so that when projecting, in this case, to the second component, but it could be whatever we like, we extract exactly what we want. Okay. So it's not so complicated, but it's putting together a few ideas like this memory and this memory, more or less. Now, a few final remarks, because I think this is the first project of a few that we will need to actually understand these kind of networks, is that the first comment is that I relied on very restricted sets of gradient steps in this constrained universality here. In particular, the first three components are very constrained. But of course, that's not needed for the universality because that's needed only if we want to guarantee all these functions are 1-Lipschitz. But if we allow for the set to be intersected with C1, as we did before, then we could just relax this constraint and take them as generic gradient steps. And then the second aspect, which I would like to improve on, even though I think I'm quite happy with this result, but I would like to improve on this, is that to get the universality with fixed width, we had to modify our architecture. We had to introduce affine layers in between the residual ones. Now, that's not necessarily a problem because it's quite common in neural networks to alternate residual maps and affine transformations. But it's somehow not as satisfying as saying, actually, it's enough to use our Euler steps, in the sense that our starting point was the dynamical systems perspective. So this is a bit going away from that dynamical systems perspective. It's not really a flow map doing all the approximation, but we have to alternate with change of variables, essentially, these affine transformations. And in fact, if we reduce them to the identity, we just get strict subsets of the two sets of functions we studied in the two parts of my proof. And we are not able to show the universality of these sets because the proof heavily relies on the affine layers. Then also the ReLU function is fundamental, of course, here, and we are not the only ones using it for approximation theory because it's a quite convenient function to work with. It allows us to essentially recover a lot of very well-studied set of functions from numerical analysis and approximation theory, and then inherit their approximation properties. So that's one of the values. But in general, we could essentially extend this for any kind of activation that either allows to exactly reproduce the ReLU function, of course, but that's a very, very limited, I think, like leaky ReLU can do that. But I think it's not it's not a very big relaxation here. And if we approximate it, that's also fine, but then it's hard to guarantee the 1-Lipschitz property afterwards. And then the final remark, because like this paper, we submitted it to NeurIPS, and of course, the first comment we got was about the experimental evidence that these neural networks are practical, essentially. And so for the residual layers that we started from in the first part of the presentation, those are layers that we already studied in the past. So we know that they are quite flexible. They can be trained with a few tricks somehow to train them as sensibly. The other one is that it has some additional layers, but we also tested them on simple toy problems, and there's no real limitation in these architectures. But in general, the only thing we need to train them and constrain them is just being able to control the spectral norms of the affine transformations. And that's fine using a projective gradient descent like approach with a power method, which can be efficiently implemented because you can uh, jump start the iteration somehow, having a lot of those steps as initialization to get a good approximation of the singular vectors, and then just use them as initial guesses for during training. So it's quite efficient there. So yeah, this is everything. If you want the slides or the paper, you can find them here. And thank you very much for the attention.
Yeah, thanks a lot. It was really interesting talk, to be honest. Where's the reaction button? Wow, cool. Yeah, it's pretty cool. Yeah, maybe I have like one or two questions. Yeah, so one question. Okay, to be honest, okay, first of all, I just want to say like the proof technique is really cool, and actually like the yeah, I guess all of the supporting techniques from dynamical systems is quite nice because at least when we try to prove stuff for when we prove stuff for vanilla relus, in some ways, yeah, it's a bit, the proofs are completely different. So they, actually, your
Yeah.
approach is pretty cool. And I really like the lower bound. It's really quite nice. Like explicitly related to number of pieces. I know that's my only comments, which are good ones. Um, yeah, there's one question. So if you wanted to extend, especially since you're like using dynamical systems or like ODs basically, um, how do you handle like lower regularity stuff? Like, could you like holder or like subholder
Uh,
with this strategy? You know?
I mean, if you mean lower than even Lipschitz regularity of the vector field, like
Yeah, yeah,
discontinuous
like a square
or
root function or something.
yeah,
So I was trying to think of like the most reasonable holder or like or a
yeah,
random motion path or something. You know? Um,
yeah. I don't know.
no, 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 me neither, me neither. I was thinking about. I mean, I know how, but not with this technique.
Yeah. Okay. Because like at least to guarantee the one Lipschitz structure of these gradient steps, you don't need too much in the sense that you
Mm.
essentially need the convexity of the function, right? Of the
I,
potential here.
I have a question. If you somehow randomized,
Mhm.
like instead of having like residual networks like this, which you added like a say like a random Gaussian
Uh-huh.
bias, yes, with a properly scaled variance. So essentially, you're doing like a Euler-Maruyama kind of step instead of Euler step. And
Okay.
you yeah, so then you converge on S like basically like a path of an SD. Would you able to go to lower regularity like that? Um, because then yeah, because for example, like SD paths are almost surely so like one half holder or worse, depending what you do to the noise. You know, I don't know,
Okay.
just an idea to have like, but
Yeah,
they're
that
pretty
could be
cool.
a way a workaround to the problem, yeah.
Yeah,
Yeah,
cool.
I'm not too expert of SDs, but
Fair enough. I'm
yeah.
not expert about these, so um, yeah, I think I had another question too, but yeah, I think that was the main one.
Yeah, so you
But
mean lower regularity for the right-hand side, essentially here.
hmm?
Your question was about having lower regularity in the vector field here.
Yeah, or at least like the ultimate like the flow map, I guess, you know, or like the not the flow, but
Yeah.
some whatever comes your object, um,
Okay.
you know.
Yeah, now I see.
Yeah, yeah, exactly. Because like I don't know how to do stochastic. Sorry, differential inclusions. Maybe there's a way to do that, but I don't know how that works at
Yeah,
all.
I mean, that's a bit funny because we are working on a separate project on no smooth neural leads.
Really? Oh, it's really
So
interesting.
so try to understand what happens essentially if instead of ReLU here you have some non discontinuous function.
Okay.
So
Cool.
some piecewise affine vector field, for example.
Cool. Cool.
And yeah, of course, there you need some different notions of solution. You might have sliding modes. You don't have uniqueness, backward uniqueness of the solution.
Oh
So
yeah, yeah,
it's
yeah.
much more complicated to study and also to simulate when training it. So that's the main challenge.
Yeah, yeah, yeah. Okay, well, I mean, I'll keep an eye out for this. Also, oh yeah, I remember the second question now. Is so you made different comments throughout the talk about like actually even right at the end about different activation functions other than ReLU and how
Yeah,
that's challenging.
yeah,
Um, I saw this paper, I think in 2023, that did this very intuitive idea,
okay,
where it's a classical approximation kind of result, no constraints, you know. But the idea was basically they wanted to transfer the results from ReLU to general active or like relatively general activation functions. Like there's some things that don't work, but whatever. But those things are known, whatever. Pretty much everything that people care about works. But the idea is essentially that they just approximate they pick an activation function and they approximate it by like a small ReLU network, and then they just
yeah,
replace the ReLU everywhere with like this fake ReLU block. Could you do the
okay.
same if your activation function is one
Yes,
Lipschitz?
so yeah, that's what at least what we wrote. I can
Oh,
show
okay,
you
okay.
here.
I didn't
Uh,
read. Sorry.
no, yeah, it's a new addition that we did
Okay,
in
okay,
the
okay.
end, in the sense that in principle one could do that and
Yeah,
still get the gradient structure. It should be
yeah.
somewhere
That's what I
here.
imagined actually, right? Yeah,
Yeah, so you could still say instead of having ReLU, I approximated with a single little layer shallow network
yeah,
based on any non-polynomial activation somehow, and then
yeah,
you still get universality, right?
yeah.
Um, and it's still a gradient. The main problem I see here, we have not developed this too much, so I cannot say this for sure.
Yeah.
But the biggest problem is that even though you know that you can get as close as you want to the redo function, then you don't know if you are well behaved in terms of one Lipschitz structure.
Okay. Yeah, I was thinking maybe of the target. Yeah. Yeah.
Yeah,
Okay. Yeah. Yeah.
yeah. If the universality, I think, like based on this argument, that translates quite naturally. Yeah, I
Yeah.
agree with that. Yeah, I didn't
Cool.
know it was done before, but it's quite a natural.
Yeah, it's exactly. It's like someone eventually did it, and everyone's okay, cool. You know,
Yeah,
like the swapping thing.
yeah.
Yeah, honestly, it's a very cool talk. I'll keep an eye out for like the follow-ups and stuff.
Yeah, no, thank you very much for the invitation. It's really cool.
Yeah,
And you
likewise.
have this seminar regularly, right?
Yeah, yeah. If you want to join the mailing list, don't be shy.
Yeah,
If you don't,
yeah.
also don't be shy.
I will, yeah, I will do that. Yeah. No, thank you
Okay,
very much.
cool, cool. All right, well, I'll see you around, and I guess maybe I'll see you through Takashi somehow. And
Yeah,
ciao.
yeah, yeah. Bye. See
Thanks
you.
again.